Have you ever actually looked up at the night sky and wondered exactly how humanity transitions from just dreaming about the stars to actually becoming a true multiplanetary species? Well, welcome to this explainer. Today, we aren't just looking at a few isolated missions. We're unpacking a master flight plan. We are diving deep into NASA's comprehensive roadmap for the next few decades of space exploration, mapping out exactly how we get from where we are right now to the very edges of the cosmos. We're going on a pretty grand spatial journey today. We're going to move step by step, starting from our own cosmic backyard on the moon, extending out to our planetary neighbors, and eventually pushing our vision to the very edge of the known universe. And the crazy thing is, this roadmap isn't science fiction. It's an active, heavily engineered blueprint for the next era of human history. So, here is our flight itinerary for this explainer. We'll kick things off with the Moon to Mars strategy, leap out to Mars and beyond, search for alien life in hidden oceans, unlock the deep cosmos with next-gen observatories, snap back to protect our home planet, and finally, look at the tech powering all of this tomorrow. You'll notice how the strategy expands spatially. We're literally starting by building local infrastructure right on our doorstep and then reaching out to entirely new cosmic horizons. Right, let's dive into Section 1, the Moon to Mars strategy, building our stepping stone. For a really long time, the moon was viewed as the final destination. But that paradigm has completely flipped. The moon is now a proving ground. It is the absolutely critical stepping stone for getting to Mars. Now, what's really fascinating here is the stark contrast between our past and our future. Back during the Apollo era, the objective was spectacular for sure, but it was brief. We're talking temporary visits, short duration stays, planting flags, leaving footprints, and coming home. The Artemis era, though, it's fundamentally different. The goal now is a sustainable, continuous human presence. We're talking about permanent lunar bases, habitats, power systems, real infrastructure. It's all about learning how to survive long-term on another world, so we can eventually take those lessons and survive on Mars. So, let's break down the concrete timeline for actually returning humans to the lunar surface. It officially kicked off back in 2022 with Artemis I, which proved that the massive Space Launch System rocket and the Orion spacecraft could actually make the uncrewed journey. Next up is Artemis II in the mid-2020s. That's going to send a human crew on a journey around the moon to really test out life support and navigation. And then comes the big one, the historic Artemis III in the late 2020s, landing a crew which will include the first woman and first person of color down at the lunar South Pole. Now you might be wondering, why the South Pole specifically? Well, that brings us to our next point. To actually make a permanent base a reality, we have to use local resources. It's a concept called in situ resource utilization, or ISRU. We're targeting the lunar South Pole because its permanently shadowed craters contain billions of years of frozen water ice. Think about it. If we're going to set up camp permanently, we just cannot pack every single drop of water and breath of air from Earth. It's too heavy. We have to extract that lunar water ice and convert it into drinking water, breathable oxygen, and most importantly, hydrogen rocket fuel. The moon essentially becomes our deep space gas station. Moving right along to Section 2, Mars and beyond. Having established our lunar stepping stone, we're zooming out to our next planetary neighbor, transitioning to NASA's ultimate long-term human objective, the red planet. But here's the thing. Long before humans can ever step foot on Mars, we really need to understand the environment. And doing that requires a literal multi-spacecraft logistical dance just to bring Martian soil back to Earth labs. This is the Mars Sample Return Campaign, and it's wild. Step 1, the Perseverance rover is already on Mars right now, drilling and caching rock samples in these little titanium tubes. Step 2 requires a completely future lander to touch down, grab those tubes, and launch them into Martian orbit. Step 3 involves an entirely separate orbiting spacecraft catching that sample container mid-flight in the vacuum of space. And finally, Step 4 brings that secure capsule all the way back to Earth. It's honestly one of the most complex robotic relay races ever attempted, and those rocks could contain actual clues to ancient Martian life. I actually want to pause the narrative for just a second here to ask the ultimate question. It's the whole reason driving this next phase of our journey. Are we alone in the universe? As we prepare to jump past Mars and out into the deeper solar system, this single question fundamentally shapes exactly where we go and what we're looking for. Which leads us perfectly into Section 3, searching for alien life and investigating ocean worlds. We're moving out to the outer solar system now, where the thread of potential life weaves through alien oceans and thick atmospheric hazes. We're looking way beyond the traditional habitable zone, out to the massive gas giants. NASA is currently investigating two incredibly distinct types of ocean worlds for signs of biology. First, up top, we have Europa, orbiting Jupiter. Beneath its cracked, icy surface is a global saltwater ocean that actually contains more water than all of Earth's oceans combined. The potential for life there comes from heat generated by Jupiter's massive gravity, which might be powering deep-sea hydrothermal vents, kind of like the ones on Earth's ocean floor. Then on the bottom, we have Titan, orbiting Saturn. And Titan is just completely different. It has a dense, nitrogen-rich atmosphere and an active weather cycle, but instead of water, it literally rains liquid methane and ethane into massive hydrocarbon lakes. Titan is essentially a deep freeze model of early Earth. It is absolutely rich with a complex prebiotic chemistry that could be the building blocks of life. To explore Titan, NASA is sending one of the most mind-blowing missions ever conceived, Dragonfly. Because Titan has such a dense atmosphere and really low gravity, like about 1/7 of Earth's, powered flight is actually incredibly efficient there. Dragonfly is a nuclear-powered multi-rotor drone, and it won't just land in one spot and stay there. It's going to fly dozens of kilometers across Titan's organic sand dunes and icy landscapes, land to sample the soil for chemical signatures of life, and then take off again to explore entirely new geological regions. Just an unbelievable piece of engineering. All right, on to Section 4, unlocking the deep cosmos. We are zooming way, way out now to the very edges of the cosmos. We're shifting from sending physical robotic explorers to mind-bending astronomical observation. The absolutely crucial point here is scale. We've all heard of the Hubble Space Telescope, right? Well, the upcoming Nancy Grace Roman Space Telescope has a field of view 100 times larger than Hubble's. While Hubble spent decades mapping out tiny, tiny slivers of the sky, the Roman Space Telescope is going to capture vast cosmic landscapes in a single observation. It'll map the distribution of dark matter through billions of light years, study dark energy, and discover thousands of new exoplanets just by watching how their gravity slightly bends the light of the stars behind them. But finding an exoplanet is one thing, finding one that actually looks like Earth is a whole different ballgame. Think about it this way. Detecting an Earth-like planet is like spotting a firefly flying next to an extremely bright lighthouse from thousands of kilometers away. The starlight is literally billions of times brighter than the planet itself. To solve this, the upcoming Habitable Worlds Observatory is going to use advanced coronagraphs inside the telescope or massive flower-shaped star shades flown tens of thousands of kilometers in front of it just to perfectly block out that starlight. That is what's going to allow us to directly read the planet's atmospheric biosignatures, looking for oxygen, methane, water vapor, the literal fingerprints of life. Let's snap back to Earth for Section 5, planetary defense. Because while we expand outward across billions of light years, we obviously have to protect the beautiful world we currently call home from cosmic hazards. To really understand how we find potentially hazardous near-Earth objects, we have to look at how our tools are evolving. Historically, we've used visible light telescopes, but the big problem there is that many asteroids are dark and non-reflective. They just blend right into the blackness of space. Enter the upcoming NEO-Surveyor infrared telescope. Even a pitch-black asteroid, when it's warmed by the sun, emits a heat signature. By scanning in infrared from space, NEO-Surveyor can spot those dark asteroids that visible telescopes completely miss. It accurately measures their size, plots their orbits, and gives humanity the most valuable resource of all in planetary defense: time. Time to launch a mission to gently nudge a dangerous asteroid off a collision course. Finally, Section 6, the tech powering tomorrow. To wrap up our flight itinerary, we really need to look at the engine room. None of these expanding horizons are possible with yesterday's tools. So here is your rapid-fire summary of the real game changers. First up, nuclear thermal propulsion. Using a nuclear reactor to heat liquid hydrogen could drastically cut our travel time to Mars, which seriously reduces astronauts' exposure to deep space radiation. Second, closed-loop life support. Systems that continuously recycle water and air, meaning we don't have to haul endless supplies all the way from Earth. Third, autonomous AI and robotics. Because communication delays to Mars can be up to 20 minutes each way, our spacecraft and rovers have to be able to make smart, independent decisions and even repair themselves. Fourth, advanced spacesuits. These act as highly mobile, miniature spaceships, protecting against abrasive lunar dust and insane temperatures. And lastly, in-space 3D printing, using local lunar or Martian soil to literally print our landing pads, tools, and habitats right there on site. Wow. We have moved from the moon to Mars to the oceans of Titan and Europa and out to the very edges of the cosmos, all while figuring out how to protect our own planet. The roadmap is in place. The technologies are literally being built as we speak. So I want to leave you with this final, provocative thought. As we build these incredible tools to explore the stars, are we finally ready to become a true spacefaring civilization? The next giant leap isn't just about visiting new worlds. It's about staying there. Thank you so much for joining me on this explainer. And keep your eyes on the skies.